So let's look at a few applications of calculus, because we are going to work with the applications quite regularly. Okay. One of the first and the most frequent use of it is when we say that, or it actually just comes down to it probably 99% of the time. Yes. Oh. And that is when we say that the derivative is a formula for the gradient. The derivative is the gradient. And once you get that, it's gradient of fx. If you get that, it makes things so much simpler. And so there's two main applications where we use this derivative as a gradient. The one is with polynomial graphs. Polynomial graphs. Okay, so what do we mean by that? Well, a polynomial is an expression that, so polynomial graphs have the form fx is equal to, and then a coefficient, x to the power of n plus b, x to the power of n minus 1 plus c, x to the power of n minus 2, etc., all the way to your final coefficient. Let's just say it's z or whatever, it doesn't really matter. Okay, now so for example, one example of a polynomial graph is just a straight line. The only thing about the straight line is his highest exponent is a 1. So polynomial is a straight line is an example of a polynomial graph. A parabola is an example of a polynomial graph. Okay, and parabola will just have the 3 terms where his highest exponent is a 2. Just knock on the gate. Okay, so what we will look at is one more. We will look at the cubic. So it's linear, quadratic, and then the cubic. Cubic would be when our next exponent is 3. Now you'll notice that a straight line looks like this. A parabola looks like this or this. A cubic function then has 2 turning points. So a straight line has no turning points. A quadratic graph has 2 turning points. So a cubic graph has then 2 turning points, either like that or like that. And then we can have something with like an x to the power of 4. We'll have, so you can see this one has 1 leg, this one has 2 legs, this one has 3 legs. X to the power of 4 will have 4 legs. 1, 2, 3, 4. Like that. With 3 turning points. Okay, interesting, huh?
So what is it called?
I don't know. Cubic. Phobic. Yes, from now on that's what we're going to call it, a phobic graph. Yeah. Okay. So basically, guys, what we've done to draw all of these graphs are by finding the shape. We first discover the shape. So now, since we know we're going to be using cubic graphs or working with cubic graphs, it's going to look like this. One of these two. For me, it looks like an N and an upside down N. Okay, that's how I remember it. An N or an upside down N. This would be the shape if my largest coefficient is positive. This one upside down N would be my largest coefficient. Not my largest coefficient, my leading coefficient. The x with the highest power, his coefficient, is negative. It will have this upside down N. So that's going to be the shape. The second one is going to be the intercepts. The intercepts. Now you'll notice in all of the polynomial graphs, in the straight line, in all of the polynomials graphs, the intercept is the coefficient of the x0 term. Okay, for example, a straight line is ax plus bx to the power of 1 to the power of 0. Ax squared plus bx1 plus cx0. Okay, this is the term, that's the only one that when I make x equal to 0, in other words, I'm finding the y-intercept, but in all graphs, to find the y-intercept, I just make x 0. It doesn't matter what it is, what graph it is, I make x 0. But for the polynomial graphs, it's nice because it's always that very last term, the one that doesn't have an x. Because when I make x 0, all the other terms fall away. And he's the only one left standing. To find the x-intercepts, how did we find the x-intercepts in... what do we do to find x-intercepts? We make y equal to 0. And the moment you have that, you've got an equation. This time in cubic graphs we will have x cubed plus, so we'll have ax cubed plus bx squared plus cx plus d is equal to 0. What is this?
It's a cubic graph.
No, a graph has a y and an x, and this only has an x.
Well, it's an equation.
It's a cubic equation. How do we solve polynomial equations?
You can use the division factor.
Okay, first you get everything equal to 0. We've got that. Next, you factorize. Okay, and so we factorize. Now you'll notice that this one will always factorize into 3 brackets. A quadratic factorizes into 2. This one will factorize into 3. Now why 3? Because if it cuts the x-axis, it will cut it in 1, 2, 3 points. 1, 2, 3 points. Now it could be that I only cut it in 2 points. I cut it on the turning point and on the other leg, or I can cut it only once. If it cuts only once, it's when I cut below. In other words, my turning points are both on the same side of the x-axis. So for example, here's my x-axis and there's my turning point, and my other turning point turns before it gets back to the x-axis. Then I only have one intercept. This will be the case, or let me rather say, I will cut twice if 2 of these brackets were the same. Then I'll cut only twice. I'll cut in this bracket and in that bracket, but these 2 will cut in the same point because I cut going down and I cut going up at the same point. Does that make sense? This is called the root of multiplicity. Now it will cut only once if when I find my first factor, and now I've got my coefficient left here. I'm not going to go into that. You must know that, how to factorize this expression. Okay, that another topic. It's not part of calculus, it's part of algebra. To factorize that thing, I have a quotient left after I divide it with this one, and that's what you said. We find this quotient by just finding one x value that will make this expression 0. So let's say it's the number 2, then x minus 2 is a factor. And then I use long division to find the quotient. Now if this quotient cannot be factorized, in other words, if I take the quotient, do you guys remember the nature of roots? This thing that's left will be a quadratic expression, ax squared plus bx plus c. That's what the quotient will be. Now I must try and factorize this one into 2 so that I can get my my other 2 roots. But if the discriminant of this thing, in other words taking b squared minus 4ac, if this is smaller than 0, remember, then this thing doesn't have roots, it cannot factorize. And if that's the case, then it means that this thing turns before it gets back to the x-axis. Does it make sense? So I can have 1, 2, or 3 roots. Okay. For a parabola, I can have 2, 1, or no roots. 2 roots if my discriminant is greater than 0. 1 root if my discriminant is equal to 0, and no roots if my discriminant is less than 0. Was that okay? A parabola can have 2 roots if my x-axis cuts twice, or it can have 1 root if my x-axis only cuts, if it turns on the x-axis, then I've got 1 root. Or it can have no roots, that's when it turns before it gets to the x-axis. Now, how will I know? I can look at the discriminant. The discriminant tells me the nature of the roots. If my discriminant, b squared minus 4ac, is bigger than 0, I will have 2 roots. If it's equal to 0, I will have 1 root. If it's less than 0, I have no roots because I'm taking the square root of a negative. Okay, now the same thing goes for here. Here, okay, I will at least have 1 root. There will exist a number that I can substitute in here to get 0. Always. But there might only be 1 such number. That would mean I have 1 root, my other turning point will turn before it gets there. So let's get to those turning points. How can I get the turning points? Whether it's now in 1, 2, 3, whatever the cubic function is, how can I always get a turning point? Well done. So the first one is the shape. The next one is actually, I say intercepts. I should actually say points. I know the shape. I just need to know through which points to draw the shape. I know this thing has a shape like that. I just need to know where's the turning points. And how do I get the turning points? I make the derivative equal to 0. Now notice the derivative of a cubic function. Let's look at that. ax cubed plus bx squared plus cx plus d. If I take the derivative of this thing, I multiply 3ax squared plus bx, 2bx, plus c plus 0. You see, this is the derivative. What do you notice about the derivative? It's a quadratic. So the gradient of a cubic function is a quadratic function. The gradient of a quadratic function is a straight line. What do you think the gradient of a 4-big function is going to be?
It's going to be cubic.
It's going to be a cubic function. Okay? So let me explain what that means. If I give you the gradient, here I give you the gradient. This is the gradient. This is not the function, it's the gradient. Okay? Let's say this is the number 2, that's the number 7. What can you tell me about the original function f? I've given you the gradient. Tell me everything just from the gradient. What can you tell me about the original function? Good. Okay. Notice you're looking at the gradient. Okay. This gradient says, as I'm going here, my gradient is what? Is my gradient positive or negative at this point? This is the gradient.
Oh.
I'm not asking this thing's gradient. Is the gradient positive or negative before 2? When I'm on this side, is the gradient positive or negative? This graph is the gradient. I'm not asking the gradient of the gradient. I'm not asking is the gradient's gradient negative or positive. I'm asking is the gradient before 2 the gradient is positive or negative?
It's positive.
Okay, why?
It's not negative. There's before 2 there's 1 and there's 1.
No, that's not the gradient. The gradient, guys.
Oh, so you're describing the graph as the gradient.
The graph is the gradient. I'm saying it's a gradient. Yeah.
It's on top of that.
Well done. Before 2, I'm on top. So if I read off the gradient, I'll read off a positive answer. Which means if I'm going to draw this graph, when I get to 2, my gradient is what? Well done. When I get to 2, the gradient is 0. Again, I'm saying this graph represents, I'm not asking the gradient of this graph. I'm saying this graph represents the gradient of another graph. So when I read off the y values for this graph, I'm reading off the gradient of another graph. So before 2, so here's 2. Before 2, my gradient is positive, which means my graph is increasing. I'm going up. So when it comes to 2, I should be going up. When I get to 2, my gradient is 0. So then I should have a turning point. Because at 2, my gradient is 0. Then my gradient is negative. But all of it, negative, until I get to 7. So if this is 2 and that is 7, at 7, I must have a 0 gradient again. Here my gradient is decreasing. My gradient is negative. But at 7, my gradient must be 0 again. And then my gradient must be positive. So my graph must be increasing. Do you see that? This is fx. I don't know what the y values is. The gradient can't tell you what the y values is. The gradient just tells you the shape of the graph. And this one tells me initially my shape is positive gradient. Before 2, I must have a positive gradient. Between 2 and 7, I must have a negative gradient, which means I'm going downhill. After 7, I must have a positive gradient again, because I'm above my gradient. My formula for my gradient is positive. Paulina, you usually look much more positive than that. Is this a little bit confusing? Is it? Okay, I'll tell you what, let's do it the other way around. Let's draw fx. Okay, I'm going to do this. Fx minus 1, x plus 1, x minus 1. Let's do that. Okay? So this is what type of function is this? Cubic, because when I multiply it out, I get x squared minus 1, x minus, may as well get a plus 1. And then I get x cubed minus x plus x squared minus x minus 1. Okay, so here is my expression. Usually they will give you this and then they'll ask you, but just to draw it, I made it simple by first choosing the roots. You'll see I chose that 2 of the roots should be the same. It has a positive shape. So I know I've got a root at positive 1 and a double root at negative 1. Do you understand why I'm saying that? It's a good way you're not understanding. I've got a root at positive 1. Why do I say positive 1? Because x minus 1 is equal to 0. So x is equal to 1. Then I have these two. X plus 1 is equal to 0. X is equal to negative 1. But this happens twice. Which means, if it happens twice, it means I have a turning point there. That makes sense? So if I draw this thing, I've got at negative 1 a turning point. And at positive 1 a turning point. Not a turning point, a root. I cut the x-axis. Now, I've got a positive in here, so it must have a shape like this. So how can I draw this shape so that I have a turning point here and my other root is going through there? So either this is -1. This is not a turning point, by the way. This one is not a turning point, it's a root. Okay? Or my turning point must be here. Now, so either I have a turning point like this, and somewhere on that side I have the other turning point, or I have a turning point like this, and somewhere down here I have a turning point. Can you see the two options? I must be able to make that N shape. My turning point will probably be somewhere here rather. Which one of the two, the green or the blue, will work so that I can go through one? The green will work. So my graph will look something like this. What will be my intercept there? -1, because here's my -1. Okay. Now, what will be my other turning point? Well, how will I find it? How will I find my two turning points?
X minus no. Gradient.
Gradient. Derivative equal to 0. What is my function? So I must make this equal to 0. And the derivative of that. So it's 3x squared minus 2x plus x. No, other way around. Plus 2x minus 1. This must be equal to 0. If I do that, you will find I get my 1, I will get x minus 1. The other one will be 3x plus 1 is equal to 0. So I'll get two answers. X plus 1, and that one must be -1. So I'll get x equal to -1 or x equal to positive 1/3. Now notice here, I already have the x minus -1 as a turning point. I knew it was a turning point by knowing that I had multiple roots there, and that so that had to be a turning point. Okay, but now the other one is at x 1/3, so it's somewhere here. Somewhere here, that's at 1/3. And now I can find the y value by just substituting the 1/3 in here to get the y value. I'm not going to do that. What I want to do is I want to show you what will the derivative look like. Remember, this is itself a function. Okay? And it's the function, the derivative. Now, if I were to draw this graph, I would have to draw it with -1 and 1/3 are my roots. They're my roots. It has a positive shape because there's a positive in front here, so it's a smiling face, so it looks like this. Okay. Now this is not the original function. I've drawn the derivative. And now the derivative, what I read off here on the y-axis is not my y values, it's my gradient values. And now I see, well, before -1, it's positive values. So, well, it's getting less. The positive values are getting less, which means my gradient is positive, but it's decreasing. Do you see? My gradient is going from a big positive value to 0. You see that? And that's what we see. When it gets to 0, my gradient is 0. So look here. Initially, my gradient is steep. I'm really struggling going up this hill. But as I'm going, my gradient is getting less steep until my gradient is 0 at 1. And that's what this one tells me. My gradient is first big, but it's getting smaller and smaller and smaller until it gets to 0. Then my gradient becomes negative. but it's never a big negative number, do you see? So my gradient is never very steep downhill. If I look at it, I'm going down, but it's never steep, not as steep as that one. I'm walking, steepest is probably here, at this point. It's probably where it's the steepest. But now all of a sudden, instead of going more steeper down, it starts going positive. Now, the point where it changes from, we call this concave and that convex. Concave means I'm making this doorway, okay, this cave doorway. Convex means I'm making this V shape. So the point where the concave and convex meets, that's the steepest it's going to get, because then it starts getting flat again. You see that? Now I start getting flat again. This is called the point of inflection. That is where my gradient is stopping decreasing. Remember, my gradient used to be very positive, very steep, then became 0, then it went it even reduced even more, it became negative. But then all of a sudden it stopped doing this and started doing that. You see, it was going in this direction, and then at the point of inflection it started going in this direction. You understand? My gradient was decreasing, became 0, got to the point of inflection. Then it started doing this. Okay, you see that? Okay, so the point of inflection is then where my gradient is stopping to decrease and starts increasing. Now look at this graph. It's the turning point of this graph is the inflection point of the other graph. This turning point here is the inflection point here. Why? Because here my graph is decreasing all the time until it gets to the turning point. So my gradient is decreasing until I get there. Then my gradient is increasing after that. So guys, when they give you this, the graph of this, speak to yourself and the whole time just use the word gradient. So you're here and you see the gradient is positive. The gradient is 0. The gradient is all the time decreasing. Until I get there, now my gradient starts increasing. Because it's negative, my gradient starts out being negative, but it's increasing until it gets to 0. Look there. My gradient is negative, but it is becoming less and less negative until it gets to 0. Then my gradient starts increasing and increasing, and this thing just becomes steeper and steeper and steeper. Okay. Why steeper and steeper? Because the gradient is becoming more and more and more and more and more. Okay. Now, how do we find this thing's turning point?
How do we find this?
I want to find the gradient's turning point.
It's x equal minus.
No.
It's not there.
Can't I add the both roots and then divide them by 2 and then you get the x squared?
No, doesn't always work.
That won't work.
Does it? Actually, it should work. You're like, sorry, I lie. You're right. You could just take these 2 roots and find the center, because the turning point is in the center. Yes. So the inflection point, that's actually a good point. The inflection point is exactly halfway between the 2 turning points. But that's not what I want to hear. I'm sorry, I want to hear something specific. How do I find a turning point? Always. No.
Second derivative.
No. How do I always find the turning point?
Always, like.
Always, no matter what.
Minus b.
No. That's not the always. That's only for quadratic.
Don't I take the second derivative equal it to 0?
No, you take the derivative equal to 0. If you want, guys, if you want to find the turning point, take the derivative equal to 0. The problem is we're not working with the original. If I want to find the turning point of the derivative, I must take the derivative of the derivative and make it equal to 0. Do you understand? So in other words, to find this turning point, I must take this graph's derivative. Now this graph is f of x. If I find its derivative, it is the derivative of the derivative and make it equal to 0. So that is why the inflection point is when you take the second derivative equal to 0. So don't misunderstand. You guys had the right idea. To find the turning point, I make the second derivative equal to 0. But the point is, you're actually taking the derivative's derivative, because you're kind of trying to find the derivative's turning point. And always, if you want a turning point, you make the derivative equal to 0. Okay. Let me show you one application of this. You won't use it in high school. What graph is this? Anyone? It's sine. Notice, sine has turning points. Do you notice that? Now, if I wanted to find the turning points for sine, what must I do? I'm going to throw someone with my pen. What do you do to find the turning points of anything?
Find the x derivative.
Find the. We make the derivative equal to 0. That's it. Now, what's the derivative of sine? It does have a derivative. You don't know how I can show you the proof, but you won't understand it. The derivative of sine, in other words, if I take sine of x, the derivative of that, that's how you write it. It is cos of x. The gradient of sine is equal to cos. It's beautiful. This is powerful maths, guys. This is some of the most powerfully used maths in the world. Is the derivative of sine is equal to cos. The derivative of cos, what do you think the derivative of cos is? It's negative sine. Okay. Very cool maths. Which means that, notice, if I make the derivative equal to 0, cos, so if the original is sine, then cos of x equal to 0. How do we solve this?
Find the inverse.
Find the reference angle. For what is cos 0? Grab the calculators, that sucks. For 90 degrees. Okay, so what's the solutions? For cos, our solutions is that this should be theta, because I used theta up there. Theta is 90 degrees plus 360 times k. So at every 90 degrees, and each time I add 360 degrees, I will have a turning point. Let's see if that's true. Here's 180, exactly halfway, there's 90. That's a turning point. If I add 360, that's 450. There's another turning point at 450. If I subtract 90 at 360, I would have 270 degrees. That's the turning point on this side. Well, what about these ones? Well, you remember cos has two solutions. It has a solution theta equal to that, and another solution theta equal to negative the reference angle plus 360 times k, which means at negative 90 I'll have another turning point. There we go. Negative 90 I have another turning point, and each time I add 360 I'll have another turning point. You see, it always works for any function To find the turning point, okay, that's now if it's a horizontal or vertical, not if it's like in a circle has turning points all over the place. Every point in a circle is a turning point, okay? But even on a circle, that's actually a great way of finding the equation of a circle. Okay? For example, let's say we had to find y squared, let's say x squared plus 2x plus y squared minus 4x is equal to not 4x, 4y is equal to 0. Can that be? No, it probably can. Okay? No. Let's say it's equal to 4. I don't know. Okay? Now, if I had to find this thing's turning point, I have to find the derivative and make it equal to 0. Okay? So, the problem here, and let's just think about it for a moment. I'll take this part and I'll take the derivative, make it equal to 0. 2x. So I'm finding the derivative in terms of x, and then I get this is 2x plus 2 equal to 0. So x is equal to 1. And this one, if I take the derivative, y squared minus 4y, if I take the derivative of this thing, I get 2y minus 4 is equal to 0. So y is equal to positive 2. Now, what this means, guys, is if I draw this circle, if I find the turning point with regards to x, morning. If I find the turning point with regards to x, I am finding the and I'm making it equal to 0. I'm finding horizontal turning points. So this one has a horizontal turning point at x equal to 1. Okay, and it has a vertical turning point because when I take it with respect to y and I find the derivative with respect to y and make it equal to 0, so I just looked at this part, then I got where it will have a vertical turning point. You see that? So this will have a vertical turning point at y equal to 2. So what do you think sits there? The 2 points, the 2 turning points that I got for the circle is the center, because the vertical turning point for a circle is directly above the center. Oh, it is. Thank you. Thank you. -1. Yes. And you'll see if you do the method that we teach you is completing the square. So if you complete the square, this one is x minus 1, sorry, plus 1 squared plus y minus 2 squared, and those two, that gives you the center of that circle. But you could also just find the derivative of the x parts, make it equal to 0. That will give you the x of the center, or the derivative of the y of the center. So that's one application, guys, is finding turning points, and that's why it's so useful when we work with polynomials, because a polynomial, a cubic function has 2 turning points. So we just find the derivative, make it equal to 0, and there you go. The next one, I'm going to look at one more application, or 2 more applications. The next one is finding the tangent line. let me go on a little bit and then we can. So if we're going to find the tangent to a line, so tangent is literally what I was talking about earlier, is that gradient at a single point. So in other words, if I was standing at this point, how steep would I be standing? Or if I were to put something just touching a curve, what direction will it take? Okay, so since we already know, and if we need to find the equation for this tangent line, we know we're finding an equation that looks like that. Now if all they give me is they give me the function fx, that's now the curve, and they give me the point, let's say x is equal to a. They give me that point and they ask me to find the tangent at that point. What important fact do you think is going to be useful here? Calculus is all about one thing. The derivative is the gradient. I want two values, the m and the c. If I can find one, I can find the other one by just substituting a point. And the one that I can easily find is the gradient. Because I know that at that point, this graph and that straight line has two things in common. They have the same gradient at that point, and they have that point in common. The point lies on both. It's a point of intersection, and they have the same gradient. So all I need to know is what is the gradient of this graph at that point. That will tell me the gradient, the fixed gradient for the straight line. And then I just need to find the y value, which is fairly easy. I just substitute a into f and I find the y value, and then I have a coordinate. And that gives me the point that I can substitute to find c.
Substitute a
into the original function f to get the y value at that point. But you can't substitute into this because you don't have c. So, but you have everything of fx. But you could have substituted into this one as well if you had all the information, because they have the same point. Okay, so what will we do? To find m, the gradient for the straight line, we will simply take the derivative of f and do what? Make equal to 0. No, we're not trying to find the turning point. The turning point is where the gradient is 0. I'm trying to find a different, well, it almost looks like the turning point, but it wasn't what I was trying to do. I want to find the gradient at a point. And so I take the derivative and I substitute the x value at that point. That will give me the gradient at that point, and that gives me the gradient for my straight line. Now I've got the gradient for my straight line. So far, now I have y is equal to the derivative of a, that's the gradient, times x plus c. And now how will I get c? I must substitute x with a and y with f of a, because this point here is where x is equal to a and the y would be f of a. Do you get that? So this would be fa is equal to the derivative a times a plus c. So the whole thing together, now I've got y is equal to the derivative of a at point A, x plus c is now f of a minus derivative of a times a. So now you can just take out, group this one and that one together, and you take out the derivative, so you get y is equal to, you can actually, and let's take this to the other side. Oh, I hate saying that. Y minus f of a is equal to the derivative. I'm taking out the derivative as a common factor between these two terms, and I'm just left with x minus a. So remember that other formula that you guys often like to use, y minus y2 is equal to m x minus x2. Is that a familiar formula? This is similar. You see, because there's my y value, there's my x value. The only thing is the gradient I get by taking the derivative and substituting my x. Okay, don't go and study that. Just remember, I'm trying to find the line y is equal to mx plus c. How will I get m? By taking the derivative of f, because I'm trying to find a tangent line, so I want the derivative of that line, the function. I substitute the point that they give me, and now I have m. It's going to be a number like 2. So now you have y is equal to 2x plus c. It's not going to be weird. It's going to be a number because you took a function and you substituted a value. And now you just need c. So you just need the rest of this coordinate. You already have the x value. You already have fx, which fx is a formula for y. The derivative is a formula for m, the gradient. The original is a formula for y. And so you have x and y, which means you have a single parameter left to solve, so you substitute a point. Okay, and that's the tangent line. Okay, let's do something interesting. Let's say I tell you y equal to 2x plus 1 is tangent to y equal to ax cubed minus bx plus 3. I don't know if it's going to work out. I'm thinking it up. I say this line is tangent to that curve when x is equal to 1. Find a and b. So what I just showed you, finding the equation of a tangent line, is routine procedure. Okay? It can be complex easy if they didn't give you the y value. So usually they give you the x and the y value, then it's a routine. I mean, it's really not difficult. Find the derivative, substitute x, you've got the gradient, use the gradient in your formula, substitute the point to get c. It's standard. But now this becomes either problem solving or complex. In other words, level 3 or 4 types questions. You can give me some idea of what you can do. So we have one equation. The two gradients must be the same because they're tangent. Which means if I take the derivative of this one, it must equal the derivative of that one. And that's where I got these. When x is 1, so that's important. It's not always the case. They're not always equal. Two gradients are always equal. They have to look exactly the same. They might just be, one may be higher than the other one, but because they might not have the same position. They have the same shape. What else do they have in common? The point. If they are tangent, it means when x is equal to 1, if I substitute x equal to 1 in here and I substitute x equal to 1 in there, I must get the same answer. So if I substitute x equal to 1 in here, I get 3. 2 times 1 plus 1. And if I substitute x equal to 1 in here, I get a minus b plus 3. And now I've got two equations. Equation 1 and equation 2. Okay? To solve it, I see A is equal to B, in this case, when I solve this one. 3 on either side cancels, so A is equal to B. If I substitute that up here, then I get 3A minus, now I'm substituting B with an A, is equal to 2. So 2 is equal to 2A, that means A is equal to 1, and since they're the same, B is equal to 1 as well. So in other words, do you see how you use your knowledge, guys, in complex and problem-solving questions? It's not about doing things you've done in class. It's the exact opposite. It's using what you've done in class to solve problems. Like in this case, your problem is, well, and I know the tangent. How can I use my knowledge about tangency to equate the answers? If it's okay with you guys, let me finish up. I can rather finish earlier. The next application is specifically rate of change. Okay, so rate of change. What we mean by that is at what rate is something changing. Now that is exactly what the derivative is. So the derivative is the gradient, yes, but the derivative is also the rate of change. The gradient is the rate at which something is changing. So for example, in physics, we look, for example, at displacement. Okay, so if I look at displacement in terms of time, I would take that displacement is usually represented, I'm going to represent it with S just so that we don't get confused with X and things like that. So let's use S is displacement. Let's just call it ST. ST. I'm using ST in the same way as I would f of x. So this is not S times t. I'm saying ST is a distance with respect to time. It's a function of time. The more time elapsed, the further I'm going to go. Okay, and this displacement, you might recall, is your initial velocity times time. Now this is not maths. Okay, I'm actually now bringing it over a little bit into physics, but it's used in maths as well without needing the physics component. But initial velocity times time plus a half acceleration times time squared. Now notice what I get when I take the derivative of this. The derivative of this gives me initial velocity, because I'm now finding the derivative in terms of t. So it's a 1 times the v plus the 2 times a half is just 2 times a t. Does this formula look familiar? Forget about that part, this part. This is velocity in terms of t. The derivative of displacement is velocity. So if I give you a derivative, a displacement formula, and I ask you find the velocity after 10 seconds, you'll find the derivative and substitute 10 seconds. Do you understand what I mean? The derivative of displacement is velocity. Why? Because velocity is delta x over delta t. dy over dx. It's just not y and x's, it's displacement. Sorry, I should have change in displacement over change in time. This is rate of change. And if I want rate of change at a specific, this is average velocity, by the way. It's average velocity, and this is instantaneous velocity. take your initial velocity plus your acceleration times time. You get it? So this is instantaneous velocity. In other words, it is ds over dt, the derivative of the displacement. Now let's take the derivative of this thing again. In other words, I'm taking the second derivative, and what do I get? Again, in terms of t, there's no t here, so this one will be 0. The derivative of velocity is acceleration. You get it?
Yes.
Derivative of velocity is acceleration. That's the second derivative of displacement. So if I tell you, I give you a formula like this: St is the height above the ground of, and I tell you, so it's how high it is above the ground. Let's say 30. This formula gives the, sorry, that should be a negative, gives the height above the ground of an object that's thrown up into the air. Okay, a simple question might be, how high is it above the ground before it is thrown? How will you work it out? Sorry?
So, please repeat that question.
The first question, how high is it above the ground before it's thrown? This is a...
30. I think it's 30.
How did you get it?
Because of t is 0 before.
T0, the time, there's no time yet. So if I make T0, I see the height above the ground is 30 meters. Okay. Now I ask you a question like, what is its velocity after 5 seconds?
Substitute 5 into t. I think.
Because this is displacement.
I think you found that derivative.
The derivative is the velocity, because we're doing rate of change. In other words, that is 5t minus, sorry, not 5t, just 5 minus 9,8t. Now I can go and substitute 5 actually that's 49. Okay, so 5 minus 49 is negative 44 meters per second. What do you guys think it means if it's saying negative 44 meters per second? Why am I getting a negative answer?
Because positive says the direction upwards is positive. So.
Good, so I'm getting a negative answer because of the direction it's falling downwards. Okay? Now I can maybe ask, what is the acceleration experienced by this object? Second derivative. So I take velocity and find the derivative. That's the second derivative of t, of s.
What are you
Which,
looking for, sir?
the acceleration. Negative 9.8 meters per second squared. Now, my question would be, why is that negative? What is a negative? I think there was a question, we'll look at that just now. There was a question in the exam. And that answer would be, remember, what does the negative 9.8 mean?
Means that it's falling down. But it can also depend on what you.
Now what, if I say my acceleration is negative 9.8 meters per second. Think in terms of rate of change. No, I'm not. I don't care about the negative for now. I want to mean, what is acceleration? It's the rate at which what? Velocity is changing. So this is saying my velocity is changing with 9.8 meters per second every second. Do you understand? So every second my velocity is getting less with 9.8 meters per second, because velocity is changing in meters per second. The same goes for velocity. This means, this answer here means, every second my displacement is changing with 44 meters. So 1 second goes by and I'm 44 meters further. Do you understand what that means? Now this velocity changes all the time because there's acceleration. The next second it's going to be negative 53.8. In other words, in the next second my displacement is going to be negative 53.8 because my velocity is not constant. So my displacement is quadratic. That's maybe, before we get to the exam question, that's maybe another phenomenal result. Is, look at this. Okay, the derivative of this thing itself is a linear pattern. You see, isn't this linear? Okay. If I take the second derivative of this thing, what do I get? Remember how we find the formula for quadratic sequence? We take the second derivative equal to 2a. The second difference. The difference when we come to number patterns is the derivative. It's the change.
I was always wondering why we use 2a.
Oh,
yeah, why we use 2a.
So do you see how all of these things are intertwined? And it would be a very easy, complex, well, not very easy, a very likely complex question to combine derivatives and number patterns into one question, because it's a very similar thing. So, for example, if you wanted to know what would be the maximum value that, so you have here, for example, let's say the numbers 20, 30, 38, 46. No, 44. And I ask you, what is the maximum value that this number pattern will have? Okay. First of all, let me quickly show you a quick method to find all of these values. Now, if I say the maximum value, you have to understand that this is a quadratic number pattern, which means I'll have 20, 38, 44. At some point this thing is going to have a turning point and then start going down, which means what I'm actually asking you for is the turning point. Okay, now so we'll first need to find the constant of, well, the formula A, B and C. So here you see 10, 8, 6. I like to go one step backwards. It's an easier formula. If you just go by one step back, then this one is 12, which means this one is used to be 18. 18 plus 12 is 20 plus 10. You see what I did? There. I fooled you. I did. Okay, then this is 2, 2, 2. And then we used to say A plus B plus C is 20. 3A plus B is that. And then 2A is equal to that. Now, if you go one step back, then C is equal to 18. A plus B is equal to 12. And 2A is still equal to that. If you go one step back, the formulas is a little bit simpler. So that's why I like that. So A is equal to 1 because 2A is 2. If A is 1, then B must be 11. And C is already 18. We have that. So see how quick it is.
So why didn't they use that method in the curriculum?
In the? There's no method in the curriculum. The curriculum doesn't specify a method. The curriculum just specifies a topic. That if you learned this, is because your teacher taught you that. Or your textbook that you used a specific method. There's no method prescribed in a textbook, in the curriculum. They just tell you the topics that students must be able to do, and then you must teach them ways in which to do that.
So, for B, you said it's 11. How did you get 11?
Because A plus B is 12. If A is 1, then B is 11. See that? Okay, so now here I've got Tn is therefore equal to n squared plus 11n plus 18. So if I want to know what is the absolute maximum value that this can get, and that's maybe another topic I actually forgot about it. Maximums and minimums. A maximum or a minimum is a turning point. So if you have a function, you want the maximum of that function, you find the derivative equal to 0 because you're trying to find the turning point. But now when you find the answer here, so for example, if I take the derivative, I get 2n squared plus, this is not the ideal number, plus 11 is equal to 0. Not n squared, sorry. So I get that n is equal to 5.5. Oh, that doesn't make sense. Okay, what that means is that 1, 2, 3, 4, the next term is for term 5. The term after that is term 6. So the term that would have been in between them would have been the maximum. So if this is a turning point, you've got term 5 here, term 6 there. So term 5 and term 6 both have the same value. And it's both the maximum value. Do you understand what I mean? So there isn't a term at term 5.5. There's no term 5.5. But there's a term at 5 and a term at 6. They will have the same value. And in the middle of them would have been the maximum. But when we work with number patterns, we only work with natural number, counting numbers, which means if we were to draw the graph of this thing, we would only have points. We won't have a smooth curve. We'll have point, because we don't have any terms in between here. We only have the terms at 1, 2, 3. We don't have a term. So this is term 1, term 2, term 1.5. There's no such thing as term 1.5. So we don't have that. We would have only plotted the points. So let's go and see if that's true. So let's try substituting in a 5 here and we see if we get the same answer than at 6. T6. T5 is 25 plus 25 plus 55 is 70 plus 18. That seems too high. B 1, 2, 3, 4. That doesn't seem right. 1 is 13. This shouldn't be, sorry, this shouldn't be 18, it should be 8. I apologize. It should be 8. 8 plus 12 is 20. Sorry, guys. Okay, so C is 8. Okay, it doesn't change anything else. So 5 plus 55. If I put a 1 in here and a 1 in there, I get 5 plus 55 is 60, so it's 78. Even that seems high. I made a mistake. This is not 2, it's negative 2. A is equal to negative. And so then this becomes 13. And so that's 3, so this is 6.5. Sorry about that. Okay, so T6 and T7 will have the same value. So if I put a 6 in here, I get 36 plus 6 times 13 is 6 times 13 is 18, plus 16 is 78, plus 8. It's still ridiculously high. It's not possible. $122. It's not possible.